So we're going to wrap up the discussion of Java Semaphore by talking about some things to consider when you apply it in practice. So the first thing to note is that a semaphore is more flexible than some of the simpler Java synchronizers. For example, semaphore is more flexible than synchronized statements or synchronized methods, which have to be fully bracketed and are very limited in the operations they support, basically blocking, lock, and unlock. Likewise, semaphore is also more flexible than reentrant lock. Even though reentrant lock has more methods than a synchronized statement or a synchronized method, you can't use it in a non-bracketed way. You have to be fully bracketed for reentrant lock. Some other things that semaphores can do that make them more flexible is you can atomically acquire and release multiple permits with a single operation. So we have acquire with a permit count. We have acquire uninterruptibly uninterruptibly with a count, and so on and so forth. And as we talked about before, its acquire and release methods don't have to be fully bracketed. Naturally, this flexibility comes with a little bit extra cost. And if you look at the paths through the abstract queued synchronizer framework, they're just a little bit more expensive than the paths through the reentrant lock code. You just have to do some extra stuff because the semaphores support a broader range of use cases. When a semaphore is used to mediate access to shared resources, as we saw was the case with the Palantiri simulator application, the semaphore itself tracks the number of free resources. So thinking back to the Palantiri, the count keeps track of how many Palantiri are available at any given point in time. However, the semaphore itself doesn't keep track of which resources are actually available at any given point in time. Those have to be tracked through some other means. So for example, if you think about our Palantiri simulator assignment, we use a hash map or a concurrent hash map or some data structure along with other synchronizers like the spin locks or the reentrant locks and so on, in order to be able to keep track of which resources are actually free and which resources are in use. So the semaphore doesn't keep track of those details. It just decides whether or not someone can come in and check to see which resource is available. So kind of going back to the beach volleyball example, having the bag of beach volleyballs at the lifeguard station simply lets a team know whether or not they can play, but that bag itself doesn't tell them which volleyball court is actually available at a given point in time. To do that, you have to walk down the beach and see which one is available. Of course, you could also have the lifeguard station keep track of that information too, but the bag of volleyballs or the semaphore doesn't keep that information by itself. These mechanisms that we would use, things like a list or a hash map and so on, they need synchronization to be used correctly in a multi-threaded program, which is why we have all these other synchronizers you're learning about, like the reentrant lock and the spin lock and stamp lock and so on. Semaphores can be tedious and error-prone to program due to common traps and pitfalls. So you have to be aware of those things. And here are some of the common traps and pitfalls, which share quite a bit in common with the reentrant lock traps and pitfalls we talked about in our earlier lesson on reentrant lock. So one problem is holding a semaphore for a long time without actually needing it. So in this case, you might acquire the semaphore and then do something that doesn't require the semaphore to be held and then eventually release the semaphore. Well, you've kind of frozen a lot of other threads out from making progress if you do that. Another mistake is to release the semaphore more times than you need to. So if you acquire the semaphore and then drive its count to 0, and then you call release, 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 then the count will keep incrementing, which could actually be problematic because it'll give other threads the impression that there's more resources available to get than there really are. Another common problem is acquiring a semaphore and then forgetting to release it. So you might return from a method or have an exception thrown, which will leave the semaphore locked. And then the reason that you do that is, or one way to avoid that if you need fully bracketed behavior, is to use the try finally block, as we've been doing in our programming assignments. So even if an exception is thrown or a return statement occurs in an unusual place in a block of code, the semaphore will still get released, if that's what you need to have happen. Obviously, if you're not trying to do fully bracketed calls, then you don't have to release the semaphore. So the kind of summarized things here, semaphores are rather limited synchronizers that don't really scale to complex coordination use cases because they just keep track of counts. And if you need something that will keep track of more complex conditions, then you want to use a Java condition object. And we'll talk more about Java condition objects probably starting next class. And this will give you a better choice for complex coordination use cases. So you'll get a chance to play around with these things. And by the time you're done with assignment 2B, you will have had a chance to apply a Java reentrant lock and a Java condition object to implement a simple form of semaphore, which will give you much better insight as far as how things actually work in practice. So that's the end of the discussion about semaphores, and hopefully this will give you a better insight to how to implement the upcoming assignments.